Probably the rain, huh? It's a little bit unexpected. Okay, maybe I can cheer you up with some things. So let's just recap where we're at. We were studying this normal mean analysis, and we've said a lot of stuff pretty quickly. We've inserted a lot of ideas, just kind of at a conceptual level, and there's lots to answer about these things. Ultimately, what I want you to understand is just the calculation details. You know, can you do all this stuff? And we're prompting a lot of conversations at once. So things that we haven't discussed that we do need to discuss, and I'm going to try to motivate basic ideas that seem abstract through examples. So I'll let them kind of pop up, and then we'll address them. So thank you for the patience for some of you that are asking me things like, what the heck is that? So mu lives between negative infinity and infinity. I understand the idea of a uniform distribution, but how do you have a uniform distribution between negative infinity and infinity? Somebody tell me, why is that impossible? That can't be a probability distribution between negative infinity and infinity.
Doesn't integrate to 1.
Doesn't integrate to 1. So if you integrate any constant, same shape, it's flat, and you integrate that constant between negative infinity and infinity, what is that number? It's not a number, right? It's like, I don't even know what that is. You say equal to infinity, I'll accept that. But that's not what you actually mean. It's this thing that it has infinite mass under it. That's not a probability distribution. So we motivated an idea of something that we're using the format of Bayes' theorem, but we're using it to something that's not quite a probability distribution. And I can either accept that and just go, okay, I don't really care. So all I thought about was likelihood times some regularizing function. I don't care if you like to think of that as Bayes' theorem, or if it's just likelihood times a penalty. So it's penalized likelihood in some sense, but I'm going to interpret everything at the end of the day as a probability distribution. So in some sense, we're motivated by Bayes' theorem. We will address this. So I think probably today we'll say some stuff about this right here, but right now there's an open-ended question about this. And does that bother you? This stuff used to bug the heck out of me. So now I'm used to it. And so let's just look at what we got at the end of the day. So we are computing this posterior distribution. We have n IID data points from this distribution. We're going to say we know sigma squared, which is a little bit far-fetched, but we'll get to inferences on sigma soon enough, sigma squared or some function of sigma squared. But we're going to compute this posterior distribution. How did we do it? In the first place, we wrote down the likelihood function. Pow, right here. So how did I think about this likelihood function? I said I knew a couple things. And some of you might know this stuff as well. That x bar, so just the arithmetic mean, sum of the xi's divided by n, I goes from 1 to n, that's the sufficient statistic for mu. If you knew that, that's all you need to know, and that's the likelihood you need to build up. If you didn't know that, you might think this is a huge step. If you want to know more about that technicality, take stat 5114 in the spring, and I'll tell you all about that stuff. That's probably where a lot of you got that from, if you already know this, and this is a little bit slow. But I just took the sampling distribution for x bar, given mu, in sigma squared. So that was the sampling distribution, and then I thought about it not as the sampling distribution, I just wrote it down that way, and then I thought about it as a function over mu, and that's the likelihood on it. So this is the sampling distribution for x bar. Some of you will know that it's also normally distributed. X bar has the exact same mean, and the variance is a little bit different. Let's just check that out real quick. So the expectation of x bar, some basic stat 101 type calculations that you might do. Expectations, sum of the xi's divided by n. Also press my indices just to save a little bit of job. So this is a linear operator. That's a linear operator, so I can exchange them. So this is going to be sum. I can drag out the n as well. So I'm going to drag both of those outside. Expectation of xi's. All the xi's have the exact same mean. It's an IID distribution, so that thing right there is mu. So this is sum mu divided by n. Sum mu is n mu divided by n. Those cancel. So the expectation of x bar is exactly the same as the expectation of the original data point. It's one reason we kind of like x bar. So it does tell us a little bit more than just giving us back the original answer. It takes out variability by averaging. And that's why we like averaging. So the variance, sum of the xi's divided by n. These are all IID, so I can just bring that sum out in front. If they weren't IID, I'd have to think about the covariance between everything. There's no covariance between points. So variances are quadratic functions, so just as a reminder, variance of a random variable, I'll say of x, is just equal to the expectation of x minus its expectation squared. So expectations of squared functions have something to do with variances. So when I pull this thing outside of the variance operator, that thing gets squared. So if I had a constant over here, now we're taking my random variable and now we're dividing by some constant, I can pull that constant out, 1 over c squared, if that was a c down there. So that just gets squared out by the definition of variance. So this is just sum of the variance of the xi's divided by n squared. We know what the variance of the xi's are. Everything's IID. They have the same variances. And so this is going to be sigma squared, summing up n times, dividing by n squared, sigma squared over n. So that's the variance of x bar. And that's what we put in here. And you might figure that sum of the xi's is a linear function, linear combinations of normals or normals. So this is a normal. So if you knew all that stuff, you would just jump right to it and invoke it. If this is kind of new to you again, you might want to go through first principles when you derive your answer. So I could have just started with this. I know what that variance is right there. I know where it's all centered. So that's what I'm plugging in right there. Or I could have started from first principles and just built up this likelihood. We spent like 10 minutes showing that those two things were proportional to each other, and it doesn't matter which one you work with. We were able to conclude by using kind of the simpler version of the likelihood that doesn't have a lot of products. Just write down our posterior distribution is this thing. And if we use the flat prior, that would just be 1. This one would disappear right here. That's a constant. I don't even need that. I would stare at this thing right here. This is a distribution on mu. So that's why we're putting it to the left of the bar. So this is a probability density function, and it looks like this. And I can recognize by its canonical form, this is a normal distribution. That's what normals look like. Where do I look for the mean of the normal? I look for it as the thing next to the random variable. Bayes' theorem has changed what the random variable is. That's what Bayes' theorem does. And here's the variance right here. And that's how we usually recognize that. That's what we wrote down even over here. If we were just dealing with the individual data points, the mean is there, the variance is there. I want to point out, if we were doing inference on the variance parameter, sigma squared, we would have just made a huge mistake. That this likelihood function and that likelihood function are not proportional to each other in terms of the variance parameter. And you can recognize that almost instantly just by seeing this parameter is appearing here only once, and here this is getting producted up n times. So there's a fundamental difference between those two things. So, but in terms of the mean, this doesn't have mu in it, and we can just forget about both of them. But if we were operating on sigma, and we threw that thing away, or we just used these two different forms willy-nilly and thought we were going to get the same answer, you're going to get different answers. One would be correct, one would be wrong. So you would get the correct answer with this one. So So that's kind of some of the advantages of just building things up from first principles. Let me go through building this distribution up from scratch using that likelihood in a minute after I tell you everything. But just to point out, this right here, if I just stare at it, I could figure out what the normalizing constant is by looking at what the parameters underlying that distribution are. This is a normal with mean x bar and variance sigma squared over n. So that's the posterior distribution. So what does that mean? That means you now have this curve centered at x bar. I always like to write it in as the square root of the variance right there. It's just the way I like to look at it. I have this distribution, and this is telling me this curve is modeling our beliefs about mu. Keep in mind, this is a posterior distribution over mu. The argument is mu right here. So this is a probability distribution of where we believe mu is going to live. So that's kind of cool. So not everywhere on the whole number line. A priori, we thought anywhere. Then the likelihood comes in with its data and says, well, I guess anywhere. These aren't actually hitting the boundary. They do float off to infinity and negative infinity, but they place so little mass out there on the tails that you might make statements like, if I looked in this region, I could add up 95% of the area, and I could describe these bounds, A and B, as bounds of belief, of where I believe mu lives, but I'm only 95% sure mu lives there. So Bayesian would interpret this as a belief interval. So where they believe mu exists or lives, what was used to sample the data. And what we've already seen, or at least we kind of believe, this thing is going to get peakier and peakier and peakier as n gets bigger. Let's just look at the equation. It's always going to be centered around x bar. X bar is going to be honing in on the truth. Why is that true? X bar as n gets bigger hones in on the true mean. Law of large numbers. So that's what means do. So and it's going to be bouncing around the truth in a normal fashion with a variance that's getting smaller and smaller as n gets bigger. So that's going to make this thing collapse and get taller and taller. Same behavior that we saw before. So in some sense, this is like a Bayesian central limit theorem. So I didn't need to know the central limit theorem for any of this. I just used the normality of the xi's themselves. So it's not even a central limit theorem, it's exact. So I will point out, you've probably used this distribution before for developing intervals. If you check real quickly in your Stat 101 class, the 95% points right here would correspond to x bar plus about 2 standard errors. The standard error is just the square root of that thing, and minus 2 standard errors. 1.96 would be a better approximation. 1.96 isn't the exact number either. So we would get the same interval, but we would have a different belief about this. We would be making different statements, I would say. The Bayesian would say it's a belief statement about where mu lives, where the non-Bayesian might say, oh, this is a statement about the process of collecting data and obtaining random intervals and seeing whether or not they covered the truth. So if I went out and I collected intervals over and over and over again, let's say 10,000 of them, about 9,500 of them should cover the truth. It begs the question, for any given interval, what does it mean if you just have one realization? The Bayesian, however, says, forget about all that. My interval has the same coverage properties, is the frequentist, but I'm also going to interpret it that mu lives in here with probability 0.95. So I think in some sense the Bayesian is giving you a lot. But it's just in terms of interpretation and what you might be able to say and get away with in a classroom. Okay, you might not be impressed by that. You might say that was a lot of thinking for an answer I already knew. So we will get to answers where Bayesians and non-Bayesians disagree with each other. So personally, I really like it. So I like to understand disagreements. Let me tell you a fact about normality first. So just fact about normality. So very typically, when I'm just trying to not talk about everything else that I've written on the board, very typically I'll use z as an arbitrary random variable, just to tell you some aside facts about distributions. So this isn't Bayesian, this is just facts about distributions. So I'll change my notation ever so slightly, but if you're like me, I can only think of mu as the mean of a normal distribution in sigma, because everybody in the universe seems to adopt that convention. So this looks like this. Sigma e to the minus 1/2 z minus mu sigma squared over sigma squared. So we've already talked about this a lot. If this isn't branded into your brain, let it be now. So that's what a normal distribution is. If you can't remember it, I recommend a tattoo. So probably be pretty cheap. I saw somebody tattoo the singular value decomposition in a theorem on themselves one time, and they said, fair game. So no points taken. Anyway, that's a normal distribution. There's the mean, there's the variance. Let's recognize it just a little bit differently. So I'm just going to expand everything. I'm going to write this down, e to the minus 1/2. I'm always going to keep that minus 1/2 locked out in front. And I'm going to expand the square. So this is going to be z squared over sigma squared minus 2z mu over sigma squared plus mu squared over sigma squared. So that's what that looks like. So everything I need to know about the distribution is found up in this part. It's the part that relates the random variable to all the parameters. Keep in mind the random variable is not in this part. This is just normalizing everything so that it integrates to 1. Doesn't have anything to do with z per se. All the z's are up here. So when we're thinking about a distribution, we need to identify what is the random variable, what are the parameters. So my notation is explicit about that. That's the random variable. Here are the parameters of the distribution. If I want to understand the parameters of the distribution, I could recognize this as a perfect square and drop it right back into that format. If it wasn't a perfect square and I had done a whole bunch of proportionality along the way, I might be throwing things away. You can remind yourself how to complete the square. It's not that difficult. So if you had something that wasn't a perfect square and you wanted to recognize which normal it was, you would have to complete the square. I'm not going to teach you to do that. I'm going to teach you how to recognize it in expanded form. So we're able to recognize where the mean is there and the variance is there. That's pretty easy. So let's just try to recognize it somewhere else. If I looked at this term right here, it doesn't have the random variable in there, and it minces 2 pieces of information. So in terms of the sampling distribution with this is the random variable, this is just a constant. I would agree, if you have your Bayesian hat on, be more careful. That might be a random variable. But since that's the random variable, this is just a constant. And so the kernel of the distribution is described through this part, right here, because it has the z's in there. So what I'm going to do first is I'm going to look at the quadratic term. And the quadratic term is 1 over sigma squared. So it turns out, this isn't a coincidence, this happens every time with normal distributions, that I can recognize the variance by looking at what's multiplying the quadratic term. And all I have to do is take that thing multiplying the quadratic term and invert it. So the variance of z is equal to 1 over sigma squared inverted, which is sigma squared. So that's my trick. Now it's easy to recognize right here. You know what it is. It's already sigma squared. Why did I do any of this? And it's because if we don't recognize what it is just by glancing at it, this is how we would recognize it. Find the quadratic term, invert that term. So keep in mind, I didn't say divide by that term. And the reason why is in a high dimensional case, that thing will not be a scalar. So you have to be a little bit more careful in that. So you would have some sort of matrix way of expressing this. So in high dimensional cases, I'll just write this down. This would probably look like this. So you'd have the Z transpose, you would have your sigma matrix in here. This would be inverted right here, and you'd have Z again. So this is in high dimensions. That's what a quadratic term looks like. And your variance would be the thing that's wedged in between that quadratic. So this is a quadratic if these were vectors right here. If everything was scalar, these would combine and be a Z to the squared term. So just something to think about for later. Don't divide by a matrix in my class. So I won't appreciate it too much. This is the -2 linear term. So I'll say -2 linear. And it has both the mean and the variance there. So if you do this in order and pluck off the variance and you know what it is, you can go to the -2 linear term and multiply it by that answer, and it'll give you the mean back. So this is just an algorithm. It works every single time. So I take the -2 linear term. That's going to be mu over sigma squared. And what I do is I multiply it by the answer that I found right down here. In high dimensions, if that's a matrix, be careful you're multiplying by the correct side. There's only going to be one correct side. Make sure that you're conforming on the right side. If it multiplies on the right, it can't multiply on the left for you. So we'll go through that soon enough. So I'm just going to grab this thing, and then I'm going to multiply it by the variance of Z, which is equal to sigma squared. And then I'm going to get mu divided by sigma squared times sigma squared is equal to mu. So I'll get mu back. So all we did is just find a way that instead of writing everything down like that, we can work with it in an expanded form and recognize the mean and the variance. Go to the quadratic term, make sure you've combined all the quadratic terms. The inverse of that thing that it's multiplying by is the variance, then take that thing and multiply it by the -2 linear term. Make sure your -2 is there. If you're missing it, it's probably because that -1/2 isn't there. So just be careful with that.
When would it not be clear from looking at just the quadratic, the Z minus U thing? When would it not be clear what it is?
Yeah, let's do an example in a moment.
The subtraction.
Let's wait for an example and see if we can do this together. So maybe it's so crystal clear I didn't need to tell you any of this stuff. We'll see in a second. But I would say the example I'm going to think about is doing this example but using the conjugate prior. Now I'm going to have two quadratic things that are going to combine and I need to do some algebra. So that's what we'll do. Let's do something else first. Oh, by the way, I've erased it off the board. I'm going to circle back on this. I'm trying to say a lot of things all at once, so I'm just interchanging the order in which I say it in until we finally all are on the same page. I'll come back to what an improper prior is, but an improper prior is a prior that does not integrate to some constant. So it blows up to infinity. It's not normalizable. This is an improper prior. Bayesians like them so much that they decided to name them. So here's just a heads up. Usually in unbounded spaces, at least for one-dimensional analyses, the priors that you would probably want are priors that do not collect too much mass in one place. So otherwise we're going to be injecting too much information, so there's some notion we want our prior to be diffused. And usually the priors that people have used are so diffused that it puts mass so, it spreads it all across the space in a way that it's not normalizable. So very often Bayesians will utilize improper priors. We'll come back to that point after we finish the conjugate analysis, and I'll connect the conjugate analysis to the improper prior. Let's just build this up a different way. So method 2. So if you haven't taken a full-blown inference class, you don't know about sufficient statistics, you didn't recognize you just need X bar, that's one-dimensional, where all the Xi's are n-dimensional, you can simplify the analysis and do it in one step, you might go through everything from first principles. So I might build up the likelihood from scratch. I'm writing it this way to denote that that's the variable of interest. It's not a random variable. Likelihoods are not probability distributions, and not all likelihoods can be normalized either. So this one can be normalized. So don't let that fool you. Likelihoods are not probability distributions until we hit them with a magic wand called Bayes' theorem. So this is going to be proportional to I goes from 1 to n, 1 over 2 pi sigma. We'll get rid of that part in a second. E to the minus 1/2 xi minus mu squared sigma squared. So let's just forget about all that stuff that we did over here. We'll still use the same prior. I think writing the likelihood down 2 different ways wouldn't encourage me to think about the prior differently. If we are following the vernacular, this is supposed to model what you think before you've seen the data. So if you glance at the data first to encode your prior beliefs, you've probably overweighted something in your analysis. I'll come back to that point later. Okay, get rid of that. Now I'm just going to work through this thing. This is going to be e to the minus 1/2 sum of the xi's minus mu squared over sigma squared. So I'm getting a little bit lazier and not writing down my indices. So now I'm going to expand the square. E to the minus 1/2. I like that minus 1/2 thing. I always just leave that lingering out in front. Just like in the beta analysis, I leave those minus 1s hanging out in front because I need them there to recognize which distribution it is. Now I'm going to just expand the square. I'll leave the sum outside temporarily. Xi squared minus 2xi mu plus mu squared. And this is all divided by sigma squared. So now I'm going to remind myself that my posterior distribution is going to be proportional to my likelihood times 1. That's my prior. So my posterior distribution is proportional to this. So this is going to be equal to e to the minus 1/2. And I'm going to drag that sum across, and I'm going to break this into 3 different terms. So this is going to be sum of the xi's squared over sigma squared minus 2, and I'm going to be a little bit careful here, and I'm going to bring this mu out in front. Now they're scalars, so I can just swap those around. The multiplication of xi into mu or mu into xi, it doesn't matter which order I do this in. When we do high dimensional analyses and these are vectors, we'll need to be careful. But right now, we don't have to be careful at all. I'm just going to interchange the order of those 2 things because I like seeing my random variable out in front. So this is going to be sum of the xi's divided by sigma squared. So the sum just went inside, hit that sum of the xi, that's right here, and I put the mu out in front. So plus, I've got this sum, it's going to come and hit this mu squared right here. This is a constant, it doesn't have any indices, and And so this is just going to be n times mu squared over sigma squared. And so my posterior distribution using the flat prior is proportional to that. Now we might use our trick. So I would agree, maybe completing the square here is way too obvious and you just do it, but we'll see a slightly more complicated analysis in a second. But let's just use our trick real quickly. What does this term tell us? Does this tell us where the variance is? Is this going to help us? What's the random variable? Mu. So common mistake. What's this term telling us? Almost nothing. So I'd have to do a little calculation right in here, but this is part of the normalizing constant. The quadratic term is here because mu is the random variable. Easy mistake to make when you're moving between sampling distribution and probability distribution. I believe the notation will help you. So that thing's on the left-hand side of the bar, that's the random variable now. We've been consistent about that, so we're going to look at this term. This is all part of the normalizing constant, so I could just write this up to proportionality and shut that. So always keep in mind what the random variables are and what the parameters are in that part of the analysis. Easy to forget, but if your notation is constantly reminding you, maybe you'll remember. So what I can look at is this is the quadratic term. I could rewrite this a little bit, put this n down here, that's exactly the same thing. And now I can tell you what the inverse of the thing is that's multiplying the quadratic term. So the quad term, and now I'm just going to inverse it so that I can recognize the variance. And this is going to be the variance of mu given x and sigma squared. And that's going to be 1 over sigma squared over n inverted, which is just sigma squared over n. Same answer we got before, but we had to do a little bit of algebra because we were working in the product form of the likelihood. So boom. Now let's go to the -2 linear term. That one's easier to recognize because there's only one thing right in there. So, and I've got -2 linear times my variance is going to be equal to sum of the xi's divided by sigma squared times sigma squared divided by n. So that came from here. So I just took this thing and I moved it there. Sigma squareds cancel, and this is sum of the xi's over n. That's x bar. Same answer we got before, but we didn't need to know a bunch of stuff to concoct this answer. Let's do it one more time. I'll probably do it in high dimensions for you and do a couple integrals for you eventually, but eventually I'm going to expect you to remember this stuff and it's almost automatic to you. And I'll find out through quizzes and midterms. So I would suggest practicing this. Okay, back to an earlier conversation. What's the conjugate prior for mu? And this question's been answered, but indulge me.
Normal.
Normal. How do you tell? Can't tell until you write down the likelihood function. So remember what the likelihood function looks like. It looks like this. So I notice, in terms of the likelihood, mu is a quadratic form in e to the minus. So e to the minus some quadratic form. So it has that shape, and I know e to the minus quadratic form is always a normal. So I might be inspired to think about, what if I picked a normal? and multiplied them together. I'd get e to the minus quadratic form times e to the minus quadratic form. That's e to the minus quadratic form. That's a normal. Prior is a normal. Posterior is a normal, i.e. it's conjugate. I know no other way than doing that. It's just thinking my way through it. Trying a couple things. If you don't know what your distributions are, you almost have no chance of being able to get these right. So we'll be doing this on distributions we'll be becoming more and more familiar with, so you'll be able to identify these answers. So let's just check. So answer, normal. So, and I'm going to write this down as a normal, and I'm going to say it's centered at mu naught, and it's got some variance. I'm going to call it v naught. I could call it sigma squared naught or something like that. A lot of times when I'm touching variances and I want to distinguish them, I usually give them slightly different notation. I don't like that square up there because it looks like it's operating on something, but it's part of the name of the variable. So I'm just going to call it that. These are the hyperparameters. So what do they look like? Just looks like a normal distribution. So how might I interpret this? This is where I believe the answer might live in some sense. So you might think of Bayes as a sequential updating scheme that I start with prior, and then I update my beliefs. And then I have my posterior beliefs after I see data. So if you like that sort of nomenclature, it's easy to recognize here that I start with some beliefs about things and I update to some new normal. If you don't like thinking about it that way, this is where I want to place weights. I'm placing weights around mu naught. I think the answer is somewhere around here. And I'm going to weight the answer by this term. That's a v naught. And following my convention, that's sigma v naught. Okay. You might not like any of that, and probably your biggest questions are how do you pick that and how do you pick that? Which one do you think is more important? Who thinks the variance is a more important thing to specify? 1, 2, 3, 4, 5, 6. So who thinks the mean is the more important thing to specify? I should know the answer to this already. Am I alone? I feel alone. Who thinks the mean is more important to specify? One person. Okay. So we'll get these things to add up the entirety of the class eventually. One of these days I'm going to have you vote. I'm going to make sure you do it. So we will have a couple lectures like that. In some sense, maybe that is. But of course, that's the location of the distribution, so we're weighting everything towards this location. So you could argue, in tandem, they're pretty important. So, but I would probably agree with that being more important. So, and I'll say what I mean after we go through the preliminary analysis. Let's just pick those as placeholders, see what happens, and see how it influences the analysis. Conjugate analysis. We haven't answered the question on how to pick those. Obviously, they will influence the analysis. Let's have a glance at how they influence everything, and maybe that'll give us some insight on how we should pick them. So, pi mu given x and sigma squared. And I would probably agree that this depends on mu naught and v naught as well. Those are our hypers. Nobody ever writes this down. They often won't even tell you that. So, but I never see that written. You might want to write it down if it makes a difference. So I almost always think about, well, I always think about when somebody does a Bayesian analysis, How would that impact things? And if I don't know the answer, I ask about it. And if they tell me it doesn't, I want them to demonstrate it. So otherwise, I just don't believe them. I've seen way too many times people say it doesn't matter, and it does matter. So don't get bullied too quickly on these things. So this is just going to be proportional to the likelihood. That didn't change. And my prior. So I'll say pi mu conjugate. And this has some parameters in there. I'll write it out like that just to be really explicit. So this looks like this. E to the minus 1/2 sum I goes from 1 to n xi minus mu squared over sigma squared. I could have used the other form of the likelihood to make my life a little bit easier, but this is in the spirit of we don't know anything right now. So we're just going to write down the likelihood. Why do we take that product? Because everything was IID, and I just put the sampling distribution in it, and then I thought about it as a function of mu. So same likelihood we had before, and this is going to be times a normal distribution. 1 over 2 pi. This would have v naught square root in there. E to the minus 1/2. Mu is the random variable, minus its centering parameter, its location, divided by v naught. So, and I can instantly see that doesn't have anything to do with mu right there. I've already written this down up to proportionality. This symbol doesn't really mean that much to us. So I'm going to toss that and just start throwing away normalizing constants. Let's combine the terms. This is e to the minus 1/2. I'm going to keep that pulled out in front. When I combine these two things, they both have an e to the minus 1/2 out in front. So that's going to pertain to both of them. Now I'm going to combine the two quadratics. So this is going to be equal to, I'll just write my first quadratic here. Sum I goes from 1 to n. I'll be really clear about the bracing of all of this. This is going to be xi squared minus 2 mu xi plus mu squared. These are all divided by sigma squareds. Close that bracing, plus the quadratic for this. So this is going to be sum mu squared minus 2 mu naught plus mu naught squared, and these are divided by their variances. So that's what I'm left with. I can do the same thing, combine all these. So this is going to be sum of the xi's squared, sigma squared, minus 2 mu sum of the xi's over sigma squared, plus n mu squared over sigma squared, plus, I'll leave this one exactly the same, minus 2 mu naught over v naught plus mu naught squared over v naught. E to the minus 1/2, all of that stuff. So I think I've taken care of the sum, and I've written this as the combination of two quadratics. Let me just ask the question. How many normalizing constants are sitting up here still? How many things can I throw away? Let me just run through it. Can I throw this away? No. That has the random variable sitting right there. So if I throw anything away that contains the random variable, I will have made a mistake. Everything else I've already written up to proportionality, so anything that's a constant I can toss. How about this? I can toss that. I can factorize it outside of that exponent and throw it away and handle that just with another proportionality sign. So I better not throw that away. How about this? Can't throw that away. It's got the random variable in there. How about this one? Can't throw that away. How about this one? Can't throw that away. How about this one? Toss. Mu naught, V naught are constants in the analysis. There are things I needed to encode my prior with. I had to pick those numbers. So I can get rid of those. This is going to be e to the minus 1/2. I'll keep that out in front. And I'm going to have a couple different terms in here. I'm going to have a mu squared term. And I'm going to have a -2 linear term. That's what's going to appear. So let's just collect all our terms. For mu squared right here, I've got 1 over sigma squared over n. That's this one. Check. And then I also have this one right here. So plus 1 over V naught. Those are both of them. Check. So for mu, I've got 2 terms as well. I have this one, sum of the xi's, over sigma squared. And then I've got one right here, plus mu naught over V naught. Now I can recognize what this distribution is. So this is a normal because it's e to the minus quadratic form. It's quadratic in mu, which is our upgraded random variable by Bayes' theorem. In this case, it actually is Bayes' theorem. The prior I picked is a proper prior integrates. It's a probability distribution, and I'm using Bayes' theorem, just as Bayes wrote it down with probability distributions. So we'll just figure out what the answer is real quick. So we know the answer, given x sigma squared, and I'm going to omit the hyperparameters because most people don't write them down, but they won't fall out of the equation. They're still there, and you should still pay attention to them. This is proportional. This is going to be equal to some normal distribution. It's going to have an expectation. I'll give it some notation. Expectation of mu given x and sigma squared. And it's going to have some variance as well. This will be the variance of mu given x and sigma squared. So I'll notate it that way just to show this is a posterior expectation and a posterior mean. And I'll be really explicit about which posterior it is. So just the expectation and the variance from those things. The variance is easier to recognize first. In fact, I would argue it's the only one you can recognize first. So variance of mu given x and sigma squared, we recognize right here. So 1 over sigma squared over n plus 1 over V naught. Inverted. So I'll give that a little bit more notation. I'll just call it V star. So that's our variance. Notice what happened. The variances didn't add together. The inverses of the variances added together, and then it got inverted again. So that's kind of interesting. Does anybody know what we call this, the inverse of the variance? It's called the precision. So this is the prior precision. So for a very variable, the inverse of it will be small, and we're very precise. So let me say that again. If the variance is really small right here, this number is going to be big, we'll be very precise. So these are the sums of 2 precisions. Let's just write down the expectation. We'll come back next time, and we'll think about what this has to do with the flat prior analysis. So this is going to be equal to myself just a little bit more room. This is going to be the -2 linear term right here. So E star is going to be sum of the xi's divided by sigma squared plus mu naught divided by v naught times that, our variance. Inverse. Here's what I want to leave you with. This is a weighted average. That's all it is. So what are the weights in front of some of the xi's? It's 1 over sigma squared. This has an n in here. So this is a weighted average with our prior belief, where what are our weights? It's the inverse of the variance. So the weight is the precision, and then I'm going to normalize by those weights. Let's come back next time and think about that interpretation of the analysis. So a lot of people will write down this formula differently. If you go to Wikipedia, you'll see something that involves all of those. You can verify to yourself they're exactly the same answers. Same answers that they give you in the book. But I like writing it down like this because it has that weighted average interpretation. So the posterior analysis is a weighted compromise between what comes from the likelihood function, that's this stuff, and the prior. And then we normalize by those weights. We'll come back next time. You can think about in a moment what happens if this thing gets big. And by big, I mean take a limit of it. So maybe take a limit, and next time we can come back and think about that limit as well, and how that corresponds to the flat prior analysis. Lots to think about. And then I want to spend a little bit of time talking about transformation of variables. We're going to be doing that a lot in this class. I want to make sure that we're all on the same page with it. So we'll do a few examples, and then if there's more questions, the review session on Thursday would be a really good time to get that rock solid, so that when we get to midterm time, taking a transform is like a great relief to you. Sweet. So I'm just going to go into cruise control. This is just a calculus problem. I don't even have to think about it. And in 2 minutes, I'll look at the answer and I'll start thinking again. So that's where I hope we'll be by the end of this week, or maybe the end of next week. Thanks, you guys. That's it for now, and I will see you on Wednesday. Beliefs, probabilities. So how strong do you believe something? Some people think about probabilities in that manner. You know, calibrating probabilities to your own belief system. Some people calibrate probabilities to frequentist systems. And some people have the ability to do both. And Bayesians have the ability to do both. So anyway, it probably has something to do with my prior as well. I wonder if it has any frequentist coverage properties. That'd be something to inspect. So what I'm basically saying is this is what we think about as Bayesians, you know, and that's what this whole class is about. So we're kind of just talking about beliefs and probabilities casually. But at the end of the day, this is going to represent your belief of where mu lives, given the data you've observed and all of the known things. Whether or not you've written them down in the equation or not, some people are pretty lazy and they'll leave that stuff out, and you have to look at the equation to understand the meaning. We were right in the middle of this example. So just a quick point, when we were working out this posterior distribution, we made a slight error right here where we put the n under there. I just can't help myself. So I know it appears there eventually. So maybe what I meant to put down is x bar n right here, where that's the sum of the xi's, but I've just introduced a new n, so I have to cancel that out. Sum of the xi's over n. How do I get the n in there? I multiply by n as well. We'll look at that in a second. Bless you. Sum of the xi's. So that's where we were in the conjugate analysis. We're going to go through this. We're going to look at what the answer is. We glanced at it last time. We'll talk about it a little bit more this time, and then we'll introduce a new concept called an improper prior. And we've already played around with that flat prior over negative infinity to infinity. It's not a probability distribution, but it's taking the place of that placeholder in Bayes' theorem is a probability distribution. We'll see what it has to do with probability distributions, if there's any connection and we can think about it in any particular way. Then I want to go through transformation of variables real quickly, different ways to think about transforms, and this is meant to be a review. So this is stuff that they would have taught you in your probability class. So we'll just recap it, make sure everybody understands how they work, why they work. Basically, this is the formula that's written down in all kinds of different books. Where does it all come from? We'll discuss it. So we'll derive it a couple different ways. We'll show you that ever since you took Calc 1, you've been playing around with that formula. So whether you know it or not. Okay, let's just come back to this example. So we're just going to finish this up and recognize this. Again, it's e to the minus some quadratic. What's the variable of interest? It's mu, so I have to think about mu in terms of its minus 2 linear terms and its quadratic terms. And they all appear here. So there's the minus 2 linear term, there's a quadratic term, there's a quadratic term, there's minus 2 linear term. And so those are the things that are going to help us to understand what the expectation and the variance of that normal is. So it's enough to say this is normal because it's e to the minus some quadratic form. So I'll ask you on a homework, how do you know something's normal? That's coming up in a future homework. And you'll probably be like, how far do I need to take this? Do I need to take work it all out by scratch, or can I use these new tricks you've taught me? And I would say basically you have to take it one step to recognize that the kernel of the distribution is e to the minus quadratic form. How do you prove that? I kind of think of it as how many times do you need to do it before you're like, it never changes. If I take e to the minus quadratic form and I multiply it by e to the minus quadratic form, it's e to the minus quadratic form. Could you make a proof about that? Of course you could. So it's never going to change. So do I need a proof? Not really. As long as you're capable of explaining the prior's normal, the likelihood's normal, and I multiply those together, it's e to the minus quadratic form, so it's normal, voila. So that'll be a good enough statement for a future homework. I think that's something you'll do on homework 3. Right now, we're going through all the gory details and working through it from scratch. So just as a prelude, I'll teach you faster tricks to do these problems later on. Okay, so what we just do is we combine, so I'll just write down this proportionality sign again. I'm going to toss this out. I can factorize that out of the equation. It has nothing to do with mu. And I can get rid of this. This has nothing to do with mu as well. So I factorize those away. They're sitting outside of this function that I'm going to write down right now. And instead of writing them all down, I'm just going to write under proportionality because this is a function of mu. So I'm going to get rid of everything that doesn't have it in there. If you want to leave it in, go ahead. It won't help you, it won't hurt you. So as long as you've got plenty of chalk and lots of time to write things down. So e to the minus 1/2, I always keep that out in front. I usually have my mu squared term out in front just because it doesn't have the dangling minus sign out there that confuses me. And as soon as I have negative, negative, I'm bound to make the same mistakes I made in college. So it's just something that doesn't go away. So watch these things and come up with devices so you don't make those mistakes. So we have mu squared, and there's two terms in here. One of them's right there. Oops, right here. So I'm going to write this down as 1 over sigma squared over n. So I've written it just a little bit differently, and I've taken that n and I've pulled it downstairs. So, and then I've got this mu squared as well. And it's multiplying 1 over v naught. And then I've got my minus 2 linear term. So there's two terms there. So minus 2 linear, there's this term, sum of the xi's, over sigma squared. I think that's where I technically made the mistake, is I just carried it over and I wrote down divided by n. So if you have that in your notes, it's just sigma squared. It's just that term sitting there. So plus the prior term. So that's going to be right here. Minus 2 linear and that involves the hyperparameters, mu naught over v naught. And that's everything. So that's all the stuff I need to know to recognize which normal this is. Now we could spend an extra 10 minutes and recap a little bit of high school stuff that you could derive for yourself and figure out if you like doing the problem that way, is you could complete the square, come up with a term that you add and subtract right here, factorize out the thing you subtract. It won't have anything to do with mu, it'll be part of a constant, and you throw that thing away and then complete the square. What I'm really teaching you is how to recognize the expanded square. And we did that before. So this is a little bit faster. I don't have to go through that extra work. So how do I recognize the variance? The variance of mu, and we'll give this a notation, given x sigma squared, is equal to the inverse of this stuff. So inverse of star. Why is that true? That was a previous lecture where we just expanded the square in the canonical form of the normal and recognized what the expanded form looked like. So the variance is the inverse of the thing multiplied by the quadratic term. The expectation is equal to this thing, the -2 linear term, times that thing. So that's how we resolve that. So this is going to be sum of the xi's over sigma squared plus mu naught over v naught times whatever this thing was. Let's just write it down. This is 1 over sigma squared over n plus 1 over v naught inverted. And so instead of writing it inverted, I'll just divide by right here. Of course, if we were in a high dimensional analysis, don't divide by a matrix. So this is all scalar form. 1 over sigma squared over n plus 1 over v naught. So I've just divided it by it or multiplied by the inverse. And so that's our answer. And the way we got that is we just started with the normal a couple lectures ago, expanded it out, recognized where those parameters were, and that saves us just a little bit of math, recognizing something just a different way. So I'll point out this thing right here, I can just write this down a little bit differently, x bar divided by n, we already did that before. So this is a compromise between your data beliefs and your prior beliefs. So it's what your answer is. So if you don't like thinking about variances and you do what most people are trained to do early on and just think about the expectation, let's think about what this expectation even means in the first place. So the expectation looks like this. So just recall a weighted average arithmetically weighting the average. I understand there's a lot of ways to average. So this is just going to be, I'll say, points. I'll just call this x1. I'll call that something different. So just z1, w1 plus z2, w2 divided by sum of the w's, 1 plus w2. We usually also make sure w1 divided by w1 plus w2 is some number between 0 and 1. W2 similarly has the same property. So between 0 and 1. So they're positive weights. And we're going to let this W1 over W1 plus W2 plus W2 divided by W1, W2 is equal to 1. You could prove that. So it's just average. So this is just weighted averages. So somebody asked me in a previous lecture afterwards, what's a weighted average? So that's what it is. There's other ways to weight and average things, but this is kind of the arithmetic way of doing it. So simple algebra. This has that form. So this expectation has that form. So I'm weighting this thing and this thing. So that's kind of where my data is centered, my likelihood is centered. Likelihood, that's coming from the prior. I'll draw you a picture of this. This is going to be a function of mu. This is going to be the likelihood function, something that looks like this. Given all of my data, sigma squared. So somebody help me out real quickly. Where does this likelihood peak? X bar. Mu is the argument. So X bar is where it peaks. This is the hardest part for people getting accustomed to Bayesian versus classical reasoning, is switching the random variable. So by the end of this, after a few months, you'll be able to switch what you think about first as the random variable. So it's centered at X bar. Somebody help me out real quickly. What is this distance that I usually draw in here?
Sigma over root n.
Yeah, sigma over root n. So that's what I usually draw in there, right there. That's how the spread of a normal is defined. And this actually looks like a normal itself. The prior looks something different. So maybe the prior is centered around mu naught over here. And it has some variance right in here, but I usually write in the square root of that thing. So it's centered somewhere different. I haven't said what those numbers are, but conceptually this is what this looks like. In this answer, the normal distribution that represents the posterior lives in the middle of this somewhere. So it looks like this. So did I draw that exactly right? I'm not sure. So I don't know what it is. So I'm not sure that I drew this exactly right. I'm not sure that the areas under all these things are 1. The likelihood doesn't need to be, but these posterior distributions need to be. But it's basically in the middle of those two things. And what's steering it towards these two different centers of retraction is not the variance, but the inverse of the variance. So the precision parameters. So those are defined right here. So let me just give you a definition real quick. Definition. Phi is equal to 1 over V, where V is the variance. This has a name. This is called the precision. So I can think about them just inversely related to each other. If you like thinking about variance, there's nothing wrong with me thinking about 1 over that thing. So the weights are the precision parameters. So it's actually the precision of the data. So how precisely we're honing in on the center given knowledge of sigma squared. So it's 1 over that. That's how this weight is coming in. So 1 over, and then 1 over V is the weight for the prior. So this analysis is weighting the precisions and those centers of attraction. And I've seen these formulas derived other places, but this gives you one rationale for deriving such formulas.
Is it okay to say that the precision of the posterior is going to be the sum of the precision of the prior and the
Yeah, because that's exactly right. And the variance is the sum of the precisions inverted. So, yeah, I think those are equivalent statements. Yeah, so that's what happens. So you will be working this out in homework 1. I ask you to just run through all of this. I would encourage you to just do it as many times as you need to before you can do it cleanly and fast. So if you're sitting there looking at the notes, all the steps, you're not doing yourself a favor come midterm time. Any questions about all of this? I have a question. How should we pick mu naught and v naught in a real analysis? I totally get it if they're just kind of placeholders and I'm trying to figure out how do I pass the exam given mu naughts and v naughts. I guess we've covered that part. Now let's get to the interesting part. What would you actually do in practice? That's my question. This is the part that everybody yells about. It's the fun part. So question, how do you choose mu naught and v naught? And I'll just kind of fill in because there's no obvious answer to all of this. It depends. So if you knew something, if you were doing like some sort of a meta-analysis, you're collecting data in one study, you went out there and you're trying to learn this centering parameter mu, and other people have done all kinds of different studies, assuming different things, collecting different types of data, but we all agree on the same parameters being measured, you might take their previous studies and look at the average of what they came up with. Now you'll have to, of course, calibrate the variance, how much you want to put on all those various studies. And you can probably do it individually and build this up sequentially and have a prior for each study coming in. So what I would encourage you is don't put so much weight on the previous studies that your prior looks like this. So you wouldn't want that to be tight. What would happen, I'd be putting a lot of precision weight into this right here. So I would end up putting a lot of weight on this term if I ended up collapsing the variance. I'm making the variance small, so the precision is getting bigger, the 1/over term. So the variance is getting small, that's making this term big. So it's putting a lot of weight on that. And so typically, good pieces of advice is make sure your prior beliefs are diffused. You want the likelihood to weigh in. So otherwise, why are you doing the analysis? So I will say, does anybody know who Nate Silver is? Several of you. What does he do? 538.com. So he's mostly a Bayesian. So he'll use formulas just like this, these weighted average sort of things. What he's usually doing is trying to figure out what people are going to predict, how people are going to vote in upcoming elections. So he's taking various polls, combining them, and placing weights on those various polls. He's also adjusting biases. So he's also calibrating this. This isn't just the average, what they might say. Might look at historical record and see they oversample in some particular way, and it's always off a little bit, but they always do the same thing, so we can forecast out of that. It's when they do something different that the polls are irrelevant. So this is about what they do. Something like this. How exactly do they adjust the means, the centering parameters of those polls? I'm sure that's like their secret recipe. So they don't tell you exactly how they do that. But they use previous data to do it. Any questions about all of this right here? So I think what we see is we have diffused prior beliefs, then the likelihood speaks loudly. If we have very, very certain prior beliefs, it takes a lot of data to overcome that. So if we think about this component, we might need n to be really big. We know what x bar is converging to. X bar is converging to the truth. So that converges to the truth as a function of n. Why? The law of large numbers. Averages tend towards the truth. So what is the variance doing? It's getting smaller and smaller and smaller. So as n gets big, this thing gets steered towards the truth. So as long as you place something plausible and you don't just make this a point mass right here by making this 0, and collapsing all your weight on this, as long as it's sensible and you've smeared mass everywhere, eventually this part of the equation will take over. So it's a question of how much data do you need to overcome your prior beliefs. Some people study that in itself. So I've seen people use these equations in ways that I never would have thought to use them. So for example, Jessica Utz over at University of California, Irvine, she studies ESP. ESP phenomena, meta-analyses on ESP, and people are pretty skeptical about all of these things. And she wants to calibrate how skeptical they are. So they say, if it's true, and there's an effect size, and it turns out it's small. It's hard to reproduce, but some people are better than others. Some people's cynicism make them like particularly not random. That's what she's told me anyway. And she says that there is a reality there, that there's probably this really small effect. And we could talk about in review session tomorrow, what are the experiments, how are they done? But she wants to calibrate how much data it would have to overcome to make a skeptic change their opinion. And it's something like they would need to see billions of studies. They would almost never do it. You just can't change their mind with data. What does that mean? Their prior belief is fixed. So they didn't smear mass very well. I call those political priors. Like, don't tell me what's happening. I already know what the truth is. I know what my policy is. So we will come up with the data that supports that. Anyway, lots of discussions to be had about these formulas, but that's how you derive them. It still doesn't exactly answer this question of how big should you make this. So we are inclined to think that this is big-ish. Somebody help me to think about what big-ish means. If I ever say big, or if I ever say small, I mean relative to something. So if anybody ever says big, it's compared to what? So sometimes it's common sense, like compared to what we're used to. But we're not used to anything here. So compared to what?
Compared to the mean.
Compared to the mean. So I will say this, I want to address that. This analysis is invariant to where this mean actually is. So remember, we don't know the mean. So we're not sure what it is, but I think what you're suggesting is we probably want this prior to overlap strongly the empirical mean. So if all of a sudden this was way off in the tails of this distribution, like in this example, then we need the variance to be big enough so that the prior overlaps the mean of the data. Now that's a little bit cheating if you really thought of it as prior beliefs. So, but I would agree in terms of practical experience, you would want that.
You kind of want to figure that your sigma over n from the data. Like,
Yeah.
not that you're looking at the data, but you want it to be larger than the kind of variability you're seeing in the data.
I agree with that completely. So I might say something like, so I think we're all saying the same thing, really. I was going to say the variance is big compared to the likelihood, but Josiah defined what that meant. So it has to do with this scaling parameter right here. So you would want this number right here to be large compared to that number. Now, if we did know what sigma squared was, if that was a reality, which is a little bit not a reality, but people do build models like this and place priors over the common sigma squared, is you might say, I want this to be equal to sigma squared. That was known in the first place. So that has something to do with knowledge. So what does that mean in terms of the weight of the prior? Combining what Josiah said. It would mean your prior was worth some amount of data points. How many? One. So it'd be like worth one data point. If I divided it by k and k was an integer, it'd be worth that many data points. Because I'm just comparing the basic form of how sigma is related to n in the original analysis and how this is related to something else. So if I ended up saying that, I'm saying the prior is worth one data point. Got to do something. So is that a sensible thing to do? It means It's a question of how fast the collection of data will overwhelm that. So if you had 2 data points, that would have a lot of weight on it. So would you ever do an analysis on 2 data points? I might. You know, I think I would ask for 3, to tell you the truth. I think that's my limit on things. We'll talk about that later. Any other comments?
So I guess I'm just a little bit confused. When you're deciding your prior not, are we assuming that you are going to have some sort of prior knowledge of how many data points you're going to get?
Yeah, maybe you know n up front.
Okay.
So, I mean, there's a lot of scenarios. You might know n, somebody walks in and says, I've got 31 data points, we're good to go. So I should be able to learn anything out of these. You're like, yeah, I'm a statistician, I read that in a book before. So you might know that, or you might actually do a power analysis up front and do a Bayesian power analysis and encode that as like, I'm gonna let my prior be worth 1 data point. Why is that good? I don't know. It's like you can't make it worth any less if you're thinking about integers. So it's a psychological thing. So we don't want it to be worth too much. What I would really recommend is if you felt like encoding this information is wiggle that thing around a little bit. That seems like a sensitive knob in the analysis. And see how varied your answers are. So when you might do this thing that Jessica talks about is, how would you scale your prior beliefs if I already know what the answer is? I see people do things like that. That's a real subjective analysis. That's like cheating. So, but there's some people call this subjective Bayesians. They come up with reasons for coming up with these things. And maybe you could rationalize it. There is a field in Bayesian statistics called elicitation. And what it means is you couch the scientist and you ask them a battery of questions and you're able to calibrate what their variances are. You don't actually calibrate their variances, you calibrate what they believe probabilities are. That's all Tony O'Hagan's stuff up in Sheffield University in the UK. I read that book too. So I think it's fascinating, it's worth talking about. I have never been successful in being able to employ that in practice. But as a philosophical mind game, sounds fun. So I can't get people to even know what a probability is when I'm just talking to them, let alone a variance. Anyway, so you get the idea, they matter in some sense, and this is a hard question to maybe answer. So how about this? If I wanted this to be really diffused, what if I made it bigger than this thing right here? I could make it bigger and bigger and bigger and bigger. It could be worth less than 1 data point. So, and I could take that concept to the limit. So if I made this prior wider and wider and wider by making that bigger and bigger, this thing would get really fat. We'll see if I can draw it. It would get low over here, and the tails look like this, and you'll have to use a microscope and figure out that's supposed to look normal. So it's just a really flat one. And if I push it way into the tails, so it'll look arbitrarily flat. It flattens out more and more. And if that variance smaller and smaller and smaller, it peaks the thing. And the opposite of peaking is flat. So I could make this really big and take this off to infinity. So that's a concept. But I almost want it to have no weight in some sense. What does that look like in terms of the prior? We're approaching a limit where the variance has to be some number to actually talk about a normal distribution. But if you did push it out to infinity, which isn't allowed for an actual normal, but conceptually I'm allowed to think about it, it turns it into a uniform distribution. The trouble with it is that it's arbitrarily close to the line 0, to the number 0. So it's getting flattened out, and it's not defined anymore. And that term for not defining it is called improper prior. But let's just think about what that actually means in terms of the analysis. So I'll just make a note real quickly that this is equivalent to thinking about pi mu is flat. Let me encode that. That means it's a constant. Since it can't be normalized in the first place, I can pick any constant arbitrarily, and my favorite constant to pick is usually 1. I'm not saying they're equal, I'm saying that's just my definition of what I'll pick. So that's what that means. And so what's kind of neat about it is it takes all the weight off of mu naught also. You'll notice as I start getting flatter and flatter and flatter, where I centered it doesn't matter. And it's gotten to the extreme limit where it's so flat that no matter where I center that thing, it looks exactly the same because it's a flat line, and I can slide it back and forth. So, which re-inspires our flat prior, this notion of location invariance. So it's kind of neat. All of a sudden, things are starting to get aligned where the limit of the conjugate prior has some really nice properties. Let's just see what the analysis looks like in terms of the mean. So the mean is right here. I'll just write that down again. X bar n over sigma squared over n plus mu naught v naught. And I'll write it in as everything in the numerator. So 1 over sigma squared over n plus 1 over v naught minus 1. Now, I don't care if you can take a limit exactly right. I might agree that this is a function of 2 things, and one of them is a ratio of the other, so maybe I need to do L'Hopital's rule. So just be really good about this and satisfy my calculus instructor. I'm going to do this even faster. But you probably need to be a little bit more formal about this thing. But I think you guys can all see this. As V naught gets big, this thing is getting smaller and smaller and smaller until it approaches that limit. This is getting added into something, so I don't need to really worry about it. So it's not shrinking down to absolutely 0 here. It's moving towards this. So same thing happens here. This is fixed. So if you don't like my limit taking, go take some more classes in the math department, and they'll teach you how to do this exactly right. So this wouldn't fly in that class, but this goes to 0. But I know that's all true. So I'm using a little bit of Slutsky's theorem in there. So designed for something that's not Slutsky's theorem. So product of these 2 things, if they both converge to constants, then that thing converges to a constant. So we don't need to go through all of that. So what does this actually converge to? This converges to x bar n sigma squared over n times 1 over sigma squared over n inverted. I'll be a little bit kinder, and I will throw this right where it should be. Rewrite that as sigma squared over n. These things cancel each other. So this is going to x bar n. It's actually just equal. So that's just x bar. It's going towards the mean. And that's what we reached at. So if we have the likelihood function, it's centered at x bar, and I'm weighting by uniformity across the whole line. What does my analysis look like? My posterior looks like my likelihood function. And I will mention that Fisher first thought of doing that in a non-Bayesian context. So he was like, I'll just use the likelihood function as a probability distribution. Voila. And he didn't have any good reason for it. So that might bother you, might not bother you. Here's reasons for doing that. I would say anybody that uses that and does the analysis and they're forecasting based off of that probably has a pretty good tool. So is it worth quibbling about what you thought about? I think it might be in terms of, does the thought process extend to other analyses? And just always using the likelihood as the posterior is probably a bad idea, but for a location parameter it might be okay because of that location invariance thing that we've been talking about, which implies flat prior. Let's talk about transforms unless there's other questions about this.
Using the likelihood as the posterior is a bad idea when you're not dealing with the location is one of the reasons. So it sounds like you're implying if you're not dealing with the location parameter, if you're dealing with something that isn't transform invariant, that's why you don't want to use the likelihood.
That might be one reason. Yeah, that's right. And we will come to exactly that. transform invariance and what that actually means. So we'll be on to that probably at the end of this discussion on transformation of variables, but we won't be deep into that conversation for another couple of weeks. That's one reason. So I'm going to keep giving you reasons for liking things. So I kind of have this opinion, if there's like 8 good reasons and they all tell me the same thing, that feels really good. You know, if they all tell me something wildly different, I'm going to think more, or else the problem's ill-posed. Usually I end up thinking the problem's ill-posed. So we're placing constraints on the problem that aren't natural. Let's talk about transforms. I guess before that, just a quick definition. So improper prior. Have the property, and I'll call this pi theta for generality. So that the integral of pi theta d theta over the entire space of theta is not a constant. And you might be thinking, hey, this is supposed to integrate to 1, but a lot of times we throw away our normalizing constants and things like that. And so if you want to multiply this by some arbitrary number k to make yourself feel better that that's not any old constant, that that's not 1, you can do that. But basically, they don't integrate. So what I really mean is that integral, when you work it out, you're tempted to say it is infinity. But it isn't infinity. Nothing is infinity. So it's diverging to infinity. So the limit when you take this thing goes off to infinity. So it's not a constant, aka it's not normalizable. AKA integral pi theta d theta is equal to infinity. I don't mean it. So, but it doesn't bother me. So lots of mistakes you can make for your math professors. But we can butter that up and make it a little bit more formal if we wanted to. So it goes off to infinity. So that's an improper prior. So we've just confronted our first one. We might feel uneasy about this. We might be thinking about, is it even Bayes' theorem anymore? Well, if you like thinking about limits and you like those mind games, you can think about it as, well, I used a proper prior, the normal prior, and then I walked that thing out and I took the limit of it later on and saw what the posterior converged to. So I used the limit of conjugate proper priors. And it resulted in something that was improper at the end of the day. At the end of the day, you don't base your analyses off of the prior per se. A lot of it should be driven by the likelihood. So I'm not going to tell you what my prior probabilities are off of this improper function. I can't do it. But I can tell you that the posterior here is proper because it's a normal distribution and I recognize it. So that part is proper. So posterior distributions that are improper are nonsense. Nobody's done anything for anybody yet. So they might have some shape, but they can't talk about probabilities. So if you ever want to mess with somebody at a conference, go to them, look at their long-winded Bayesian analysis, and go, I think your posterior is actually improper, right there. And they will know. If that's true, you're a host. So yeah, you probably have a mistake in your code, and then walk away. So I guarantee you that person will be rattled all day about that. And they'll be seeking you out, like, are you just messing with me? Okay. Improper priors may be okay. We like the answer that we're getting, and we're questioning whether or not it's Bayes' theorem, but we have a lens to look through, the limit. Let's look at transforms. Usually you'll see something like this. You might have some distribution a disk on theta, so I'm going to be specific about this, and I'm going to say P theta is P is not any old P, it's the special distribution that pertains to theta. So very often people will bold that to tell you that's the random variable, the space in which points here are being evaluated. So this is meant to describe a density function. So I don't mean disk, I mean density. So say you have some density like that, and you have some relating parameter. That if I have theta, I can tell you this other parameter phi, and I tell you phi, and you can tell me what theta is. So if you have that mechanism to go back and forth, function is bijective. You tell me one, I tell you the other. So you can do this. You can work out the distribution on phi. I'll be specific, these two p's are not the same. The notation almost makes it obvious. So we want to be a little bit careful in all of this. This is going to be p theta, evaluated at theta, d theta, d phi. So that's usually what's presented to you in a calculus book, or I should say in a probability book. And I've seen lots of derivations of this. I've seen some that don't help me to understand how to actually work problems. So, but they're technically more accurate than what I would probably tell you in the next couple minutes. We'll at least get through one explanation of where this formula comes from. So just be really clear about this, what we're actually talking about. Let's give these symbols a little bit more meaning and show what the explicit connection between phi and theta are. So let g theta, a function of theta, equal to phi. I just pick these numbers arbitrarily, or these parameters arbitrarily, theta and phi, and I'm going to switch these on you 2 more times in this lecture just to get you used to these formulas. I'm going to use x and y, I'm going to do something and something else also. Make sure that we've got this, make sure we can use this formula in both directions, that it doesn't really confuse us. So I'm going to make an assumption right now. This assumption is required that G inverse exists. And that's equivalent to saying, you tell me theta, I tell you phi, you tell me phi, I tell you theta. So they have the same information between them. So just like the variance, 1 over the variance, I can tell you the precision, tell me the precision, I can invert that and tell you the variance. So that'll probably be our first application of this formula. So that's maybe what you want to think in the back of your mind. So g theta is equal to phi right here. So that means that I can invert this function, theta, is g inverse phi. If you can't do this, you need to break it up, the problem, into sections where you can do the inversion. So that makes problems usually a little bit difficult. So, but we'll keep it simple and conceptual for now. If you want to know about problems where g inverse isn't explicit and you can't write it down as just one formula, maybe you have to write it down as a set or something like that, ask me in review session tomorrow. So we will do a review. I think I said 6 p.m. here. So in this classroom. Just make that review tomorrow. 6 p.m. Within reason, I'll stay as late as you can. So usually until like 7:30 or 8. It's usually when people have their fill. We can make it real quick if we have no questions about anything. Okay, so if you want to know if in problems like G inverse doesn't exist, I'm happy to work those out for you and show you examples that look like that and show you how you derive the transformations. Usually you have to add together 2 things when that happens, and it's an application of the chain. So let me just be real clear about this. If I'm trying to figure out the distribution on this thing right here, I'm going to write this down, P phi. What am I going to do in my formula using this formula right here? I'm going to grab the function p theta, whatever that function is. So I've apparently got some math right here, and it's a function of theta, and I can look for that. And instead of plugging in theta, I want this thing to be a function of phi. So I want to talk about theta in terms of phi, and so I'm just going to do the inversion right here. So since I can talk about one or the other, because this is a bijection, I can just write down G inverse phi right there. It's not good enough to do this. I've taken the theta, thrown it in right there. It looks like the same formula, but you have to be a little bit more careful because you've changed the whole space you're working in. And so you need to adjust for how you warp the space, and how you warp the space has something to do with G in the first place. So I'm going to end up writing down G inverse phi d phi. This is equivalent to writing down theta. G inverse is theta, so those are equivalent formulas to each other. This is true. This is true in calculus. This makes a little bit more sense to me when I write it down this way. This is how I'd actually compute a problem. So if I were trying to do a transformation, I'd grab the argument of whatever the function I knew, and I'd write down that argument in terms of the parameter that I'm going after. Since this has to be a function of that parameter over on the left-hand side, there's only one thing to throw in there. So if you have any thetas over here left over, you've made a mistake. This has to be a function of phi as well. So I need to take my derivative with respect to phi, because this thing has to be a function of phi, because this is a distribution of phi. So mechanically, it has to be that way. So I think what I'd like to do is next time, come back, see who understands this already, knows how to use this formula, and based off of what I find out, I can decide which lecture I want to give. So, does everybody understand what I just said? I think so. Cool, right on. I will see you guys on Friday. We will be prepared to answer some questions about transformation of variables. Yes, please.
Are we still having quiz on Friday? Or?
You heard me. You heard me correctly. That is what I said. So usually, I'll just give you guys a heads up when I say, does everybody understand what I just said? It always means the same thing. Does anybody know what it means? Help me out. It's on the quiz, it's on the test. I will find out. So, anyway, yeah, I think so. So, the spirit of it is attendance, just to make sure everybody's involved in class. Also, I can give you feedback right away. So, if you totally blow the quiz problems, it won't make an impact in your grade so long as you take the quiz. So, and then get the immediate feedback, and then we can correct everything. So, try a problem like that if you need to glance at your probability book tonight. So that might be a good idea. So I've been doing this so long that I know how to drive that formula in lots of different ways and how to utilize that formula. I will point out, in high dimensional space, this is going to be a determinant. Absolute value of the determinant is what we're actually representing right here. So there's a Jacobian term, and I often say Jacobian. In one dimension, it's just a derivative. So we'll talk about the high dimensional analog, but I'm only asking you about the one dimensional case right now. Here's a very good question for you. Why the absolute value? We'll come back next time and answer that question. Okay, thanks a lot, you guys. I'll see you all on Friday. I'll have both videos up later this afternoon.